A point of inflection is a point on the curve where there is a change in concavity around it. You can see a point A on the left, the curve is concave down, and on the right, it is concave up. Now this point A is a stationary point of inflection because its first derivative is equal to 0. So is its second derivative. We have another point of inflection over here at B. Once again, you can see this tangent at point B is parallel to the x-axis. We may also have a non-stationary point of inflection. There is a change in concavity, but the tangent isn't parallel to the x-axis. To find the point of inflection, we need to first find the second derivative, equate it to 0, and solve for x to determine its location. Then, to confirm that it is a point of inflection, we need a table of test points to check the concavity. If there is evidence of change in concavity, then we have a point of inflection. Let's look at this example where we are to find the coordinates of any stationary points, points of inflection, and the intercepts with the axis. For y is equal to x into x minus 6, all things squared. The easiest is to find the x and the y-intercept. To find the x-intercept, we let y is equal to 0. We get these coordinates. To find the y-intercept, we let x is equal to 0. Then we need to find the first derivative, y dash. I'm using product rule over here, and I get y dash is equal to x minus 6 into 3x minus 6. To find the second derivative, it's easier for me to first expand the first derivative and write it as 3x squared minus 24x plus 36, and then use power rule. I get y double dash as 6x minus 24. Now to find the stationary points, I need to use the first derivative and equate it to 0 and solve for x. This will give me the solutions of x, or the solutions of y dash is equal to 0 will give me the position where I could possibly have a minima or a maxima. I got two solutions over here, x is equal to 6 or x is equal to 2. Now to check the nature of the 2 points, I can either use a table of test points or use the second derivative. I'm using the second derivative over here. At x is equal to 2, the second derivative is negative, therefore it's a maxima. At x is equal to 6, the second derivative is positive, so we have a minima at x is equal to 6. Remember, in the question we are asked to find the coordinates. So to find the coordinates of the maxima and the minima, I sub in x is equal to 2 and x is equal to 6 in the original y to get the corresponding y values. Now to determine the point of inflection, I need to use the second derivative. I equate the second derivative to 0 and solve for x. 6x minus 24 equated to 0 yields x is equal to 4 as a solution. Then I use the table of test points. Around the critical value, x is equal to 4. So to the left, at x is equal to 3, y double dash is negative, hence it's concave down. To the right of the critical point, at x is equal to 5, y double dash is positive, so therefore it's concave up. There is evidence of the change in concavity, therefore x is equal to 4 represents a point of inflection. Once again, to find the corresponding y value, I sub in x is equal to 4 in the original y. You can check the graph over here. When you draw the graph, make sure you label these key features, which include the maxima, the minima, any points of inflection, and any x or y intercepts, as you see over here. I have added additional information to indicate where the function is increasing. The function is increasing to the left of 2 because we have a positive derivative, first derivative. Dy by dx will be positive over here, dy by dx will be negative over here, and will be positive to the right of x is equal to 6.